here we're going to try and estimate the sum n less than x of sigma 0 n. So here sigma sub 0 n is just the number of divisors of n. Now, elsewhere we estimated partial sums of sum of divisor functions with a Dirichlet character and some non-trivial argument here, but here the behavior is actually a little bit different. So it's going to be the same general strategy that if we want to estimate these partial sums, we can construct a Dirichlet series out of the things that we're summing up. And this Dirichlet series ends up being the square of the Riemann zeta function. So let's look at this integral. So it's around some rectangle, and let's take the vertices to be 1 plus epsilon minus it for some large positive real number t, and then we'll go to 1 plus epsilon plus it, and then we'll go to 1/2 plus epsilon plus it, and then 1/2 plus epsilon minus it. And as usual, we'll call this C1, C2, C3, C4. Cauchy's residue theorem says that if we take the integral along this contour, C1, C2, well, I guess C4, C3, of the square of the Riemann zeta function times x to the s ds over s, this is going to be 2 pi I times the sum of the residues of zeta s squared x to the s 1 over s. And this is going to be a sum inside C. Perron's formula says that the partial sum of the Dirichlet coefficients, which in this case is going to be the thing that we're interested in, is equal to, this times 2 pi I is going to be equal to the sum, or the integral along C1 of zeta of s squared x to the s ds over s. So to get a good estimate, we're going to have to again bound this integral along C2, C3, and C4. So along C2 and C3, the integral zeta s squared x to the s ds over s, here we can use this convexity bound. And so the convexity bound here is that zeta s squared is at most t to the, so normally it's 1/2 minus, for 1 power of zeta, it's 1/2 minus sigma over 2, and we're squaring it. So it's t to the 1 minus sigma plus epsilon, provided that, this is not negative, right? So this is going to be when sigma is less than or equal to 1. And then otherwise it's just epsilon. So this integral, we can bound it just by taking absolute values, and what we end up getting is that this is going to be x to the 1 plus epsilon t to the minus 1 coming from the right endpoint, and for the left endpoint we're going to get x to the 1/2 plus epsilon, and then we have a t to the 1/2 coming from this, but then we've got t in the denominator here, so it's going to be t to the minus 1/2 plus epsilon, and as before, we're going to find that this doesn't contribute. Sorry, I forgot the error term here. The error term here, of course, is x to the 1 plus epsilon t to the minus 1. Okay, now what about the integral along C4 of zeta s squared x to the s ds over s? Well, this is going to be t to the 1/2 using the convexity bound, and it's going to be x to the 1/2. We're integrating along t. There's a 1 over t here, so we end up getting x to the 1/2 plus epsilon t to the 1/2 plus epsilon. Balancing error terms, we're going to have x to the, so set t equals x to the alpha. The error term that we're going to have is x to the 1 plus epsilon times x to the minus alpha coming from Perron. We see that the bounds along the horizontal segments, this one is the same as the error term in Perron's formula, and this one is just going to be less than what we got along C4, so we can ignore this contribution. And here we're going to have an x to the 1/2 plus epsilon, x to the to the plus alpha over 2, and then we don't need to really have a plus epsilon here. So balancing error terms, let's say 1 minus alpha should be equal to 1/2 plus alpha over 2. That means that 1/2 should be equal to 3/2 times alpha. So that means that alpha should be equal to 1 over 3, which is typical. This is often the alpha that you get. And the error term you end up getting overall is that, okay, well, 2 pi I times the sum n less than x, divisor counting function of n is equal to 2 pi I times the sum of residues of zeta s squared x to the s times 1 over s, and the error term you have is big O of x to the 2/3 plus epsilon. Okay. Now let's talk about this sum of residues. So what's interesting here is that, so you only have one pole. And that pole is at s equals 1, but it is a double pole. So this double pole is going to give some different behavior for this asymptotic. The Riemann zeta function around s equals 1 has this Laurent series expansion 1 over s minus 1 plus, and then the constant term is gamma, the Euler-Mascheroni constant 0.577 dot dot dot, and then you have O of s minus 1. So if we want to know what the a sub minus 1 coefficient in the Laurent expansion of our product, zeta s squared times x to the s 1 over s, Well, let's replace each of these by their Lagrange series. So we have a 1 over s minus 1 plus gamma plus O of s minus 1. And then we're going to have two copies of this. 1 over s minus 1 plus gamma plus O of s minus 1. And then our x to the s, well, we can write this as x times x to the s minus 1, and we're expanding around s minus 1 is 0, so this is going to be 1 plus, and then here we're going to have an s minus 1 times log x, and then big O of s minus 1 squared. And finally, our 1 over s, this is going to be 1 over s minus 1 plus 1. So it's going to be, when s minus 1 is 0, you're going to have a 1, and then the linear term, right? So 1 over 1 plus s minus 1 is equal to 1, and then it's going to be what? Minus 1 over 1 plus s minus 1 squared evaluated at s equals 1 times s minus 1, and plus dot dot dot. So this is going to be just a 1 minus s minus 1, and then plus O of s minus 1 squared. Okay, what is the residue of this at s equals 1? So we can get a 1 over s minus 1. So we're looking at the coefficient of this thing at s equals 1. So the way we can do that is we can take an s equals 1, an s minus 1 from this factor, and then a gamma from this factor, and a x from this factor, and a 1 from this factor. Or we could do the same thing with the other factor. So take the gamma here, take this term here, take the x here, and take the 1 here. And then the last way we could do it is we could take, well, it's going to be two ways. We could take both the 1 over s minus 1 here and here, and then here we could take the x here and the minus 1 coefficient here, so this will be a minus 1 times x, or we could take, and this is sort of the interesting bit, we could take the x log x here and the 1 here, 1 times x log x. You see, this grows faster than the other stuff. And then plus whatever, the other stuff doesn't matter. And so that means that the sum of residues of zeta of s squared, x to the s times 1 over s, is going to be equal to x log x, and then the x coefficient we have here is 2 gamma minus 1, 2 gamma minus 1 times x, and then, okay, yeah, that's our sum of residues. So what this implies is that the sum n less than x of divisor counting function of n is equal to x log x plus 2 gamma minus 1 x, and then our error term was O of x to the 2/3 plus epsilon. And this is pretty cool, right? Because now we're seeing some new behavior. When we have this double pole coming from the Riemann zeta function, or the square of the Riemann zeta function, we're getting x log x growth of our sum of divisors function, right? So on average, this divisor counting function, the number of divisors of n is about log of n. And we've got this pretty cool correction term here. You know, just getting this asymptotic x log x is one thing, but getting this nice correction and this decent error term is pretty good. And we can see that this behavior is also different from what we got when we had a Dirichlet character. So previously we found that some sigma sub w n chi with some restrictions on these things. I think we ended up getting that this was L of 1 minus w chi times x, and then maybe we had an O of x to the 1 plus the real part of w minus 1 plus 2 real part of w over 3 plus real part of w plus epsilon. So here, the growth was linear in x, that this had size 1 on average, and here we're seeing that it has size log x on average. So these choices that we made, setting w to 0 and taking our character to be trivial, changed the behavior, and that's kind of neat.